Hello, let's start our AP Physics math review. Now, some of you may not have been able to see this in class, so let me give you the brief introduction of why we're doing this. There is a lot of math that we use in physics, and we assume that when you're assigned to the class, you already know how to do it. But I've learned from experience that some students need a little bit of a brush up on some of the concepts. Again, this is a review, it's not instruction, so you may find that, yeah, Mr. Robinson, I already know this stuff. So you can kind of fast forward through parts that you know cold and slow down on the parts that may seem new or need a little refreshment. Now, there's going to be 4 parts to this. Today, we're only going to be doing part 1, which is called Here Comes the Metric System. There's going to be other videos also that cover scientific notation. Part 3 will be about trigonometry, and then the 4th video will be about dimensional analysis. We'll get to it when we get to it. By the way, don't be intimidated by this diagram that I put out here. You may look at this and say it's all Greek. Well, some of it actually is Greek. That theta, those are Greek letters. I promise you, when we get to this content in the course, I'll introduce all these pieces, and this will make perfect sense to you. So don't be scared by that. It's really not so bad. So let's get to part 1 here, which is about the metric system. Now, physicists everywhere use what are called SI units. They use this in all of the sciences, so you may have seen this in chemistry and maybe bio, not sure about that, but certainly in chemistry you've probably seen these. SI stands for Système International because the French were the ones that named it, and in English that would be the International System of Units. All the SI units are based on powers of 10, which makes them easy to work with. This is a good thing. And the metric system is the starting point for all SI units. That's where this powers of 10 thing came from, is that SI units can be traced back to the metric system. And that's why we need to learn the metric system or review the metric system, because that's pretty much all we use in physics. Now, all SI units are defined in terms of each other, and that means that calculations are easier and it makes the physics much simpler to understand. Before they introduced SI units, different countries and different associations and even different universities would use different systems of units, and it made it very difficult for one group of researchers to examine and understand the work done by another group of researchers, because they were literally not all on the same page. So SI units have streamlined this and made life good for all of us. Now, what do you need to know in terms of metric system? You need to know the metric units for length, for volume and mass, and what their abbreviations are. And you also need to know the standard prefixes that go with all of those units. There's other things that are nice to know, and that is where the units came from. In other words, the history behind them and how the units are related to each other. So let's get into the need to know stuff. These are the metric units and abbreviations that are SI units. Now, there are other metric units that exist out there, but these are the ones that we care about because they've been adapted as SI units. So this SI unit of length is the meter, and the abbreviation for that is a lowercase m. SI unit for volume is the liter, which is abbreviated with a capital L. And the SI unit for mass is the kilogram, which is abbreviated as kg. You have to know these cold. Don't rely on being able to look these up. They happen so often, they appear so many places that you have to know these ones cold. Now, what about the prefixes? Again, you've probably heard of these, but you need to know what they look like and what they mean. Okay, the first one, you got to memorize these. Okay, milli, as in millimeter, milligram, or milliliter. It means 1/1000th. So when you see that prefix milli, it means 1/1000th of the base unit. There are 1,000 millimeters in a meter. When you look at a meter stick, those smallest lines, those closest together lines, those are the millimeters, and there are 1,000 of them in a meter. Likewise, milligrams, sometimes you see these in medicine dosages, 200 milligrams of ibuprofen in one tablet. That's 1,000th of a gram. A milliliter is 1,000th of a liter, and you see this sometimes in dosages for injections, like when you get a vaccination or something like that. They'll talk about so many milliliters of whatever the medicine is that they're giving to you. So milli, that's one you got to know. Next one is centa, and this one really only comes up in centimeters as a unit of length, which is 1/100th of a meter, and that prefix cent means 100. So this is just like cents, literally cents, dollars and cents. A cent, a penny in the American system of money is 1/100th of a dollar. That's why they call it a cent. A century is 100 years. So that prefix cent means 100, and a centimeter is 1/100th of a meter. Now, technically, you could use this prefix with centigram and centiliter. It's just that we don't. You never see that. Centimeter is the only one that you see, and you got to know it. Next one, let's see. I know there it is. Okay, next one is kilo, which means 1,000, as in kilometer, kilometer, or kilogram. That's where those two show up. It means 1,000 of something. Don't have any easy way for you to remember that one. That's just what it means. Now, as a side note here, we don't normally say kiloliter, though technically that's correct. Instead, we use cubic meters. It turns out that 1 cubic meter has a volume of 1,000 liters. And for some reason, cubic meters is easier to say than kiloliter. And the way we write that down is meters cubed. So that's the abbreviation for a cubic meter, which represents 1,000 liters. Who knew? Well, now you. Okay, now the nice to have stuff. Um, these are prefixes that you should recognize and have some idea of what they're saying, but it's okay if you look these up. We have the AP Gouge. It's a sheet of information that you can use on the AP exam, and all this stuff is on that. So when we start getting into problems where we use these again and again and again, they'll become as familiar as centimeters and millimeters. Yeah, just be able to recognize them and know where to find them. So mega means is 10 to the 6, which is a million. So a megajoule would be a million joules. A megagram would be a million grams. The prefix is, well, is mega. The abbreviation is a capital M. Giga is even bigger than a mega. It's a billion. So sometimes you hear about nuclear weapons being, 10 megatons or a 1 gigaton explosion from like a meteor hitting the Earth or something like that. Yeah, giga is a billion, mega is a million, giga is capital G. Going the other way, below 1, micro is 1/1 millionth, and nano is 1 billionth, or 1 times 10 to the minus sixth for micro, and 1 times 10 to the minus ninth for nano. Notice that they are lowercase. Nano is with a small n because it's less than 1. Giga is bigger than 1, so it's a capital. That's another way to kind of tip you off whether we're talking about something that's huge or tiny. The weirdest one here is the micro. That is it's slipping my mind what letter, Greek letter that is, but that you'll see that in abbreviations. That means a micrometer and nanometer. Okay, those are nice to know. You should be familiar with them, but you don't have to have them memorized. Now, personally, I find that it's easier to remember this stuff, and particularly to be able to make conversions from one thing to another, if I know the history or the story behind where this stuff came from. That's just my brain. So if this helps you, great. If not, well, that's how it is. So whose idea was this metric system anyway, and what were they thinking? The metric system came out of the French Revolution. Some people have said that the only good thing to come out of the French Revolution was the metric system. That's a matter of opinion, but metric system definitely is a good thing. The thought behind it was that the French were rejecting the aristocracy and royalty, and the idea that some people were better than other people simply by virtue of their birth. In the French Revolution, they rejected that idea. And so they wanted to get rid of weights and measures that were based on the body parts of some aristocrat. So, as you may know, the standard English foot was based on the length of the foot of the king at the time. Supposedly, an inch was the width of the king's nose. A cubit, it was the distance from the elbow to the end of the fingers of whatever person happened to be in power at the time. And I don't even say that facetiously. One of the problems with this idea of making standard measures based on the body part of the ruler is that they would change when the regime changed. And it would be different when you went from one town or city to another. An inch or a foot in one town could be different than a foot in another town, simply because the boss of that town wanted to have the foot based on him and not on his rival, 50 or 100 miles away. So the French wanted to go to a system that was based in something more fundamental. And what they chose was to define the meter as 1 millionth the distance from the equator to the North Pole. Who knew? And boy, is that trivia, because they didn't even get it right. They couldn't survey that accurately. So what they wound up doing was they just made a stick that was pretty close to 1/1 millionth the distance from the equator to the North Pole, and they called that a meter. But back then, it was literally just the distance between two scratches on a metal bar that they kept in a vault in Paris at a constant humidity and a constant temperature. And that was the meter. And it turned out to be an entirely arbitrary thing. But it was good because anybody could write a letter to Paris and they would send you a meter stick. They would send you a piece of wood that was as close as they could get to that standard meter. And the metric system was set up that as long as you had that stick, you could figure out everything else. And this was wonderful because scientists on opposite ends of Europe could check each other's work because they were all working from the same units of measurement. And as long as everybody had that stick or a copy of that stick, they were all working off the same sheet of music. And that is really, really good. So how did they work? How did it work? Okay, you take your stick. You figure out what a centimeter is on that stick by breaking it up into 100 divisions. And then if you will have a box built for you that is 10 centimeters on each side, so a cube 10 centimeters on each side, by definition, that volume of that cubic box was 1 liter. So a box 10 centimeters by 10 centimeters by 10 centimeters, that's a liter. Now, if you fill that box with water, because anybody can get water, the mass of that water, a liter of water, is 1 kilogram. So from the stick, you can go to standard units of volume and standard units of mass. Very, very nice thing to do. Now, if you do the math, it turns out that 1 milliliter of water, 1/1000th of a liter, turns out to be a cube of water that is 1 centimeter on each side. And in that case, the mass is 1 gram. Now, the French made the gram the standard unit of mass. Physicists and SI units have moved away from that, and we make the kilogram the standard unit. We found that, by we, I mean physicists who aren't alive anymore. Um, Physicists found that it was much easier to make this larger box, the 10 centimeter by 10 centimeters by 10 centimeters. You would be much more precise in building that box than building a box that was 1 centimeter by 1 centimeter by 1 centimeter. So people wound up using kilograms instead of grams anyway. Physicists did anyway, and liters instead of milliliters. So yeah, so that's the story behind it. Now, why is this useful to know? Because sometimes you'll get a problem like 14,000 cubic meters of water flow over Niagara Falls every second. How much work is done? And you say, what? Well, if you know that a cubic meter, how big a cubic meter is, and understand that from that you can figure out the volume of water and the mass of water, well, now you can get started on the problem. So understanding this relationship between volumes of material and the dimensions of those materials is very, very useful and will help you considerably. Okay, so let's wrap it up. What do you need to know? You need to know milli, centi, and kilo and their prefixes, and you need to know the SI units of volume, length, and mass, and their abbreviations. Nice to know is the lesser used prefixes like mega, giga, micro, and nano, and their prefixes, just so you can recognize them and say, oh yeah, that's a unit of measure, and then look it up and figure out what it is. And also it's nice to know how the SI units of volume and mass are derived from SI units of length. That helps you find your way through problems if it isn't broken down for you. You can break stuff down on your own. Okay, so that wraps up part one of our math review. From now on, the next three, there will be more pen and ink work, and I'll actually show you how to solve problems and all. This first one was basically just memorization, so no pen and ink work on this. Thank you for your time, and we'll see you again when you get to part two.